here's the setting for what I'll talk about. So Y is closed three-manifold. Lambda is a contact form. On Y, R is the Reeb vector field. G of lambda is a set of simple periodic orbits of R. And if gamma is a periodic orbit, then A of gamma is the period or symplectic action. There are all sorts of results about what kind of Reeb orbits exist, what are their properties, and I want to consider the following particular question about that. So we're now going to consider a surface sigma. So it's a closed surface. So it's embedded, a compact surface, I should say. It's embedded, except possibly the boundary. And I want it to be transverse to the Reeb vector field, except possibly the boundaries. So the interior is transverse to the vector field, so that implies that d lambda restricted to the interior of sigma is symplectic. And I want that each component of the boundary of sigma is, well, maps to some Reeb orbit gamma. So there's your surface. These are some Reeb orbits. And it could happen. It's a little hard to draw, but I do allow the possibility that as sigma approaches one of these orbits, it's the boundary component of sigma is going around the orbit several times. And it's transverse to the Reeb vector field everywhere in its interior. So these arise, for example, it could be, a global surface of section, or, but it doesn't have to be. I just want any surface, and the fact that the boundary is on Reeb orbits is sort of for convenience, to allow me to prove something. Okay, so then the question I want to ask is, do there exist Reeb orbits intersecting the interior of the surface? And if they do exist, how frequent are the intersections?
What do you mean by Reeb orbits?
Yeah, Reeb orbit is periodic orbit of Reeb vector field. So Do there
What's
exist?
the word frequent here?
I'll define that in a second. So do there exist in orbits like this? Could intersect many times. So if gamma is a Reeb orbit, the frequency is the number of intersections with the surface divided by the action. So that's on average, how much time does the flow go between intersections? Maybe that's the inverse of the frequency. No, I guess it's a frequency, but whatever. Anyway, this is, what can I say about this number? So there's a theorem of Fourier, which says that if limit is generic, then the Reeb orbits are equidistributed. And what I mean by that here is that for any open set U in Y, there exists a sequence of Reeb orbits gamma k such that the limit as k goes to infinity of the action of gamma k intersect U divided by the action of gamma k. So this notation, this means the amount of time that the trajectory spends inside the open set U. So this is what fraction of the time is the Reeb orbit in the open set U. And this converges to the volume of U divided by the volume of Y. Where the volume is the integral of the contact of lambda y to lambda. So that implies something about this question. So for my surface, I could take, so given sigma is above, take U to be the image of the rate flow for time in some interval from say 0 to epsilon, starting in the interior sigma. So you just you take the surface and you thicken it a little bit by saying let's start at a point and flow for time epsilon. Right? So you get this little neighborhood of the surface. And that'll be my open set U. So any time a Reeb orbit intersects the surface, it's going to go through this open set U and it's going to spend time epsilon. So if you have this equation, then that's going to tell you that the limit as k goes to infinity of the number of intersections of gamma k with sigma, or the interior sigma anyway, divided by the action of gamma k is the area of sigma divided by the volume of y. But here the area of sigma is computed with 2n. So this is what you get if you have equal distribution, which holds for generic lambda. And for this, I don't actually need the assumption that the boundary of the surface is along waveforms. So this would work for any surface transverse to the ring vector field. Now, the thing is, this is only true if lambda is generic. If lambda is not generic, this is certainly not always true. For example, you can make a surface like this on an irrational ellipsoid that doesn't have any Reeb orbits intersecting it at all. So I want to prove something which does not assume that lambda is generic. So is there any kind of existence result that we can prove without a genericity assumption? And the answer is yes, except that the statement has to be weakened slightly. So here's the theorem. So given a symplectic surface, sigma as above, the supremum over gamma of periodic orbit of this frequency is greater than or equal to this number here. And the caveat here is that gamma is allowed to be one of the orbits on the boundary of the surface. So this theorem says that there exists, like for any epsilon, there exists some gamma such that this number is greater than that number minus epsilon. But the gamma could be on the boundary of the surface. And so I have to interpret, what do I mean by the intersection number of the boundary orbits? So I can give you a more precise definition, but informally, gamma sigma dot sigma divided by the action of gamma is the frequency of intersections with sigma of a Reeb trajectory near gamma. So you start like that in this chalk. It's like the chalk paradise. So yeah, you start near the orbit, you go for, if you start close enough to the orbit, then you can go for a long time without leaving the neighborhood. And so you go for time 1 million, you see how many times did you intersect the surface, you divide by 1 million, and that's approximately what this gamma dot sigma.
So not the statement also about the linearized flow?
Yes. I can give you a more precise definition for linearized flow. So, if the boundary orbits already satisfy this inequality, then the theorem doesn't tell you anything. But if for the boundary orbits this number is less than that number, then it does tell you something. It tells you if there have to intersect orbits intersecting the interior sigma with this number greater than that number minus epsilon.
So that would be a statement ultimately. So you have the boundary orbits, and if the winding isn't, the linearized flow is too slow or something, then you must like too slow or too fast. Yeah? So it's in the direction.
If it's too fast.
Too fast.
Yeah. I guess I forgot to add one hypothesis, which is I just erased it. I'll put it here. Because this might not be necessary, it was just for my convenience. So I want to assume that the orbits on the boundary of sigma are elliptic. So the linearized flow is conjugate to a rotation. I'll move it around so once they're cold. Okay. So if you do an example, one example is worth 1,000 theorems. So let's take A and B positive real numbers and assume that A over B is irrational. And I'll take Y to be the boundary of ellipsoid EAB, which in my notation is the set of Z and C2, such that I times absolute value of Z1 squared over A plus pi times absolute value of Z2 squared over B is equal to 1. And lambda is the restriction of the standard rule for 104. So we have some from I equals 1 to 2, xi dy I minus y on the dxi restricted to the ellipsoid. The Reeb vector field on this you can calculate is 2 pi times 1 over a d by d theta 1 plus 1 over b d by d theta 2, where if z1 and z2 are complex coordinates and xi and yi are the real part, an imaginary part of zi, and theta I is the argument of zi. Okay. So this has just two simple Reeb orbits. So there's gamma 1, it's a set where z2 equals 0, and this has action equal to A. And there's gamma 2, which is where z1 equals 0, and this has action equal to B. And then I can make a surface like this. Um, so let P and Q be positive integers relatively prime. And there's a surface sigma. So you can make a surface which is a cylinder. And the intersection well, so you can think of this ellipsoid, aside from the two great orbits gamma 1 and gamma 2, it's an interval across the two torus. So if we take some part where this Z1 is equal to some constant, which is not 0, and Z2 is equal to some other constant, that is 0. So this is a two torus. So this is a curve in the homology class. P comma Q in a font of T2. And this will be a symplectic surface. Let's assume that BQ is greater than AP. So this is then sigma.
So what is C1, C2?
Just some constants.
Just some constant.
And sigma is a symplectic surface. And the boundary of sigma is Q times the orbit gamma 2 minus P times the orbit gamma 1. So I'm not gonna try to draw the fact that the boundary sigma is wrapping Q times rep gamma 2 and Q times rep gamma 1, but it is. The area of sigma well, it's just the symplectic action of this minus the symplectic action of that. So it's BQ minus AP. And the volume of Y is AB. The volume of the four-dimensional ellipsoid is AB over 2. Okay. So this magic number here, area over volume, is Q over A minus P over. Now, since there are no orbits at all intersecting the interior of sigma, then if this theorem is correct, then each of the boundary orbits, or at least one of the boundary orbits, has to satisfy this inequality. In fact, they both are an equality. So the gamma 1 dot sigma over the action of gamma 1 equals gamma 2 dot sigma over the action of gamma 2, and these are both equal to the area of sigma. Or the volume of Y. So to see, I didn't give you the precise definition of this, but I'll just tell you how it goes. So gamma 2 dot sigma well, divided by the action of gamma 2. So there's a sort of obvious trivialization of the context structure along gamma 2 given by just given by the z1 coordinate on C2. So the rotation number of the Reeb vector field as you go around gamma 1, if you look at this, sorry, gamma 2, if you look at this equation, it is E over A. But then the surface has itself a rotation number as it goes around the orbit, which is P over Q, and you have to subtract that. And then you have to, I hope this is going to come out right. You have to divide by the action of gamma 2, which is B. You also have to multiply by Q because the surface is coming, the boundary is mapping to gamma 2 with multiplicity Q. So like locally, if this is a cross section, the sort of Q branches of the surface boundary. And the rate with which you're rotating, with which the rate flow is rotating, well, as you go once around the orbit, it goes B over A, but then the surface goes P over Q. And then you have to multiply by Q. So I hope this comes out to be the same thing. So this, well, this is, so this is, I combine the fractions, it's BQ minus AP over ABQ times Q, which is BQ minus AP over AB, which is same as this. So that's how that worked. So in this example, you have an equality here. But if I change this situation a little bit so that the boundary orbits were having a lower frequency of intersection, then I would have to have some orbits intersecting the interior. That is the statement of the theorem. And the key point is that we do not assume any genericity. These things have to exist. Any questions about that?
Why do you find this number when the boundary is degenerate? Boundary orbit is degenerate.
Well, all I really need to know is that it's elliptic and has so linearized flow with some rotation. That rotation could be irrational. That's all right. So I can give an application of this. I probably shouldn't raise the theorem statement. So so this is a application. I won't give you the most general statement because it's a little complicated to state. So this is a simple, this is special case of the application. So let's say sigma is a compact surface. With one boundary component. And omega is an area form on sigma. And let's assume that phi from sigma to itself is a Hamiltonian diffeomorphism. And let's assume that near the boundary of sigma, phi is rotation by 2 pi theta 0 for some number of theta 0. And let's also assume, just to simplify the formulas, that the symplectic area of omega is equal to 1. So on the boundary, it's rotation by 2 pi, or near the boundary, it's rotation by 2 pi theta 0. Okay, so then there's a unique function f from sigma to r, such that df, sorry, I guess I first needed to say, so you can take beta, a primitive of omega, which has a standard form near the boundary of sigma. So as a function f such that df is v star beta minus beta, because well, f is preserving the cohomology class of omega. So this is a closed one form. So I can find a function f, and then I make the unique.
So if you add a constant to f, then it would still be true.
That's right. So I need another condition, which is that f restricted to the boundary of sigma is theta 0. And I define the Calabi invariant it depends on f, and it also depends on theta 0. Because theta 0 is a real number, and I could add an integer to it, and it would still be true that near the boundary phi is rotation by 2 pi theta 0. So this depends on this choice of this integer. Anyway, this is defined to be the integral over sigma of f of f. It's some real number. For example, if sigma is the disk, and f is rotation by 2 pi theta 0 on the entire disk, then the Calabi invariant is simply theta 0. So you can think of it as some kind of rotation number. And then there's the notion of mean action. So if gamma is a periodic orbit, I just have k points such that phi acts by a cyclic permutation of them. Then, so let's call this D. So the action gamma is the sum from I equals 1 to T of f of s off. And the period D of gamma is the number of points in my orbit, and the mean action is the action gamma divided by the period. So it's the average value of the function f on this periodic orbit. Okay, so then the theorem is that if the Calabi invariant is, sorry, phi, excuse me. And this is phi also, sorry. So if the Calabi invariant is less than theta 0, then the infima over periodic orbits of the map phi at the mean action is less than or equal to the Calabi invariant. So under this hypothesis, you can find an orbit such that the average value of f on the orbit is less than the average value of f on the entire surface, at least plus epsilon. So, and you can state a version of this a little more generally. You need you don't need phi to be Hamiltonian. You just need it to have zero flux so that you can define the Calabi invariant, and then similar statement holds. So then there have been various results along these lines. I might forget some of them. I apologize for any that I forget. But I proved this for the disk. And then Morgan Weiler proved a version of this for an annulus. Nelson and Weiler proved some examples of this for non-Hamiltonian, certain non-Hamiltonian maps arising from torus knots. So these examples suggest that this would be some sort of general phenomenon. Although these proofs all used spectral, they used the linking filtration and embedded contact homology. So you had to sort of compute that for these examples, and computing that in full generality seems difficult. And then there's some improvements to the disk case by Bernopasov. Graham and Bernopasov. And then there's a paper by Bernopasov and Prasad, which proves something like this in the generic case. And they also have the opposite inequality where you have the sup of this is bigger than, and it uses a version of a sort of variant of Fourier's equidistribution, which we talked about again. Anyway, so this result generalizes, well, not all these things, but a lot of these things. So this is a sort of very general phenomenon. You could ask if I could drop this hypothesis, or if I could put a soup here and put a greater than or equal here, so that is known for the disk by this paper, but in general, I have no idea. So my method will not prove that. You could ask the same question here, like, is it true that the infimum of this is less than that? I don't know. I'm a little doubtful that that's true in generality, because it has some consequences which seem a little suspiciously strong, but I'm not sure. So anyway, this theorem is a direct application of this. So given the situation of this theorem, where I have this area preserving surface diffeomorphism, if it's Hamiltonian, or more generally, if it is zero flux, then I can make a contact three-manifold, which has an open book decomposition, where the surface is the page, and the boundary circle of the orbit is the binding of the open book. And then the Calabi invariant becomes the contact volume. And this hypothesis here, that the Calabi invariant is less than theta zero, is exactly what you need to, in the corresponding statement over here, to ensure that the boundary of sigma does not satisfy this inequality, so that you actually get orbits in the interior of sigma. And those Reeb orbits in the interior of sigma correspond to periodic orbits of the diffeomorphism. So I can write that down. So we can make a contact three-manifold by lambda, where it's an open book decomposition. Where sigma is the page, boundary sigma is the binding. And the periodic orbits of lambda consists of the binding orbit together with the periodic orbits of the surface diffeomorphism. And the volume of y lambda is the Calabi invariant of the complicated zero. You might have to add some sufficiently large integer to theta zero before doing this, but that doesn't change it doesn't affect the statement of the theorem, because it shifts both sides by the same integer. And then the area, let's say when it is 1. And the way the formalism works, the intersection number of the boundary of sigma with sigma is theta zero inverse. So then, and the action of boundary sigma is equal to 1. Okay, so in that statement over there, the boundary sigma intersects sigma divided by the action of the boundary sigma is theta zero inverse, which is and the area of sigma over the volume of Y is 1 over the Calabi invariant. So the hypothesis that the Calabi invariant is less than theta 0 implies that some this thing is less than this thing. So that if gamma is the boundary of sigma, it doesn't fulfill this inequality. And so then we apply the theorem to get that the supremum over gamma periodic orbit of lambda, which is not the boundary sigma of gamma dot sigma over the action is greater than or equal to 1 of the Calabi invariant. But then this thing, this is the inverse of the mean action. So then that gives you the statement up there. Does that make sense? Ish. Questions about that?
It's a bit surprising that this is easier. It's a bit surprising that there is, that this sounds like other argument, like other thing to prove in the application.
Right. So I should tell you a little bit about how to prove this.
Yeah.
Okay, so what's the technology?
I mean, and there is, I mean, that's the only way that you know to prove this, the two-dimensional.
Sorry?
I mean, the only proof that you know for the two-dimensional application is using this.
Well, I mean, these papers used different methods. They used they mostly used the linking filtration and embedded contact homology. And this one used a version of Bayesian equidistribution, which uses something similar to embedded contact homology. And I'm also going to use something similar to embedded contact homology, although I think my proof, if at least for the parts of this that are corollary, I think my proof is an independent argument because I'm not going to use the linking filtration at all. So the idea of the proof of the Miller theorem so I'm going to use what I call elementary spectral invariance. Of the contact three-manifold. So these are numbers. The sequence of numbers that C0 of y is equal to 0. C1 of y is something positive. and then non-decreasing sequence of numbers. And it's called elementary because the definition is similar to the, well, they're related to the ECH spectral invariance, but the definition is a lot simpler to make. So they're defined as a kind of max-min energy of holomorphic curves with k point constraints. And then the key properties so the first one is spectrality. Which is that for each k, there exists a finite set if there's alpha I comma mi, where alpha I is a simple Reeb orbit. And mi is a positive integer. Such that the k spectral invariant is the sum over I of mi times the action of alpha. So each spectral invariant is the total action of some finite set of Reeb orbits, possibly with positive integer multiplicities. The second property is sort of monotonicity. It says that if f is some function of y, which is everywhere greater than or equal to 0, then so, well, the basic version of the statement is, so I can take the contact form lambda and multiply it by e to the f. I get another contact form, and that increases the spectral invariance. But there's a stronger version of this that I need, which is that ck plus l of y comma e to the lambda f minus ck of, sorry, e to the f lambda minus ck of I lambda is greater than or equal to cl alt, I have to tell you what this is, of the set of s comma y and log cos y such that 0 is less than s is less than f of y. And so this is what is called elementary or alternative ECH capacity. So this thing, this is a symplectic four-manifold. So the symplectic form on here is d to e to the s lambda. So this is a subset of the symplectization. So if I draw it like s going like this, so s equals 0, that sort of corresponds to Y. And then here I have the graph of F. So there's some region in between Y and the graph of F. So that's some four-dimensional region in symplectization. And you can look at various symplectic capacities of it. So I want to use these alternative ECH capacities. This is another kind of spectral invariant. If you just take L equals 0, then it says that it's monotone. And then the third property, so these two properties are not too hard to prove if you have the definition, which of course I didn't tell you. And then the non-trivial property is the Weyl law. Which is that the limit as k goes to infinity, ck volume lambda squared over k is equal to 2 times the volume of phi. And for general three-manifolds, the proof for general three-manifold follows from a similar statement for the ECH spectral invariant, which was proved in the paper by Dan Christopher Gardner and myself and Vinicius Ramos. If the three-manifold is a three-sphere, there's a more elementary proof of this. There's also a Weyl law for these CL alt things. So this is 4 times the volume. At least for this particular kind of example. So in this machinery, the idea of the proof of the main theorem is as follows. I actually already said I did proof of theorem. Okay, well now I told you the machinery, so I can tell you actually idea of the proof of theorem. So suppose that it's not true. So suppose that all of the orbits have lower frequency than we're looking for. Now we're gonna change the contact form. So we're going to change the contact form in a neighborhood of sigma. So if our surface sigma looks like this, we're going to take most of sigma, we'll sort of remove a little bit near the orbits. And we'll flow this for some small amount of time. So it's the flow by time epsilon. So I've sort of thickened, I have this thickened neighborhood of sigma, which is like sigma across an interval. And then I'm just going to multiply the contact form by some constant bigger than 1, multiply it by some cutoff function, so that it's 0, or so that function is 1 on the boundary of sigma. We multiply bounded by e to the some kind of function. So it comes to me. And then we're going to run out of time. Well, anyway, you can do this continuously. So you can multiply the cutoff function by some number going from 0 to 1. And as you do this, you can look at the derivative of these spectral invariants and see how much they change. And the idea is that, well, you look at like the derivative of a spectral invariant is the derivative of the contact form along some set of orbits. And if the orbits are not intersecting the surface frequently enough, then the derivative of the spectral invariant is going to be small. So if you don't have any high frequency orbits, then in this inequality up here, so this number minus this number is going to be kind of small. But then you need a lower bound on this number and you get some contradiction. And moreover, you can make it quantitative. So you can say, you can actually give an upper bound on, like, if I want to realize, if I want to get something which, so this thing is bigger than this minus epsilon, I can get a bound in terms of epsilon and these various spectral variants of how long the orbit has to be. That's the rough idea for the amount of time. So thank you.
The reason you use the elementary invariance is the genericity assumption. You want to get rid of that?
So the invariants are defined without genericity because, well, initially you define them assuming things are generic, but they satisfy whether C0 are continuous. So then they uniquely extend to the generic case. Now in this argument, there are details which I didn't have to explain. So I actually sort of do want things to be non-degenerate in order to get this argument going. But because I get quantitative upper bounds on the length or the action of the orbits that I'm producing, then I get the degenerate case also by limit of non-degenerate cases. Okay, I got that question.
And you can get rid of the elliptic assumption.
I'm not sure about that. I would presume so, but got to save something for the next paper, right? But an open question, which I really don't know the answer to, is you could say, you know, look at the set of all values of this over all orbits. Is its closure an interval? That's a question I've been wondering about.
Is the closure what interval?
So the set of all of these numbers for all orbits given. It's like all the different frequencies. Is the closure of that set some interval? I mean, it's certainly not going to be an interval. Like you can make examples where it's just going to be rational numbers in an interval, but is this closure an interval? Or could there be some gaps in there?
I'm sorry, one last other people first. So if this is elliptic, then you need assumption on your Calabi application also, or that's fine?
So in the application of the Calabi invariant, when you make that open book, the binding is going to be elliptic already because he's.
Okay, I see it. Think again.